So continuing on issues of functional form, so we briefly discussed what happens, transforming the dependent variable to turn a non-linear model into a linear model that we can estimate with OLS. You can also sometimes leave the dependent variable what it was and change the independent variable. So when might you want to do that? Well, suppose that you start with your data set and then you have some variable, say demand for gasoline, how many gasoline people purchased, and the price of gasoline, and you notice that you as good trained data scientists, you start by looking at some pattern in the data, and the first thing you decide to do is to run a kernel regression of the demand for gasoline on the price of gasoline. And then you realize that it's really doesn't look linear at all, that people have, that in some places very steep, in some places much flatter, so it doesn't look that it's going to be characterized nice. On the other hand, you wouldn't want to continue working necessarily with a kernel regression because it's a bit heavy going, it's harder to control for other things, and we know how to nicely represent kernel regression as bivariate things, but then when it becomes multivariate, it's kind of harder to look at. So you would really move to a linear model, and the question is, can you do that? Is it the case that if the relationship between y and x does not appear to be linear, can you not do OLS? And then, in fact, you can do OLS. What you can do is to try to transform the variable x from just its basic incarnation as x to something a little bit more richer in order to be able to represent the non-linearities and yet estimate a linear model. So this is why the linear model is beautiful, because it doesn't restrict us to estimate linear things. We can just modify x to go back to a linear model. So there are only two things you could do to do that, two ways to go, and I'm going to briefly talk about both ways to go. The first thing you could do is to say, as you know, any functions can be approximated by polynomials. So the first thing you could do is to regress y not on the x only, but on polynomials of x, or in fact polynomials of transformation of x's. And once you do that, you're back to an OLS. So the simplest way you could do that is to say, suppose I'm back to my gasoline example, which is actually a famous example because it's where Jerry Hausman and Whitney Newey, who are both econometricians in the department, developed a lot of the theory underlying not what I'm going to say in a few slides, which is series expansion. You run your nonlinear regression. It looks kind of funny shape, not at all linear. So then you decide to run a y on polynomials of x. Here I'm assuming that x is just a vector, not a matrix. So it's, for example, purchase of gasoline on the price of gasoline. So we have the price of a constant, the price of gasoline square, cubic, and any number you want to put in. So you could put straight polynomials in there, or you could do orthogonal polynomials, or whatever transformation of x that you want. If you assume that the model is known, for example, you assume that it's really a square or it's a cubic, then you're back to straight OLS, nothing special. You just have OLS, but your y variable is regressed on three regressors, which happens to be x, x squared, and x cubed. So all the theory that we have gone through goes through without any change. It's just that you assume that y and x are related by this particular shape. So you're good. Once you've done it, once you've estimated your polynomials, you can plot it by taking for a number of ranges, say, of the price of gasoline, the predicted value for demand based on this coefficient. You have estimated beta 0 hat, beta 1 hat, beta 2 hat, and beta 3 hat, let's say, if you have done a cubic. So you can plot it. You can take the derivative, because we know how to take the derivative of this thing, so it's very nice. So that's easy, just same. If you assume that the model is not known, in particular, you don't know what is the real functional form, you just don't know, you want to approximate it with these polynomials, then you can still do a linear model. You don't have to do a kernel regression. You can do a linear model and just add powers in x2, x3, x4, x5, etc., till you have the shape you like. And then the question you might want to ask is, well, but how many should I add if I don't know the... does anybody has an idea of how many you should add and how we should even think about it? When do I stop? So if I know the shape, I know it's a cubic, I just put a cubic. If I don't know the shape, then when do I stop adding polynomials? Yeah, go ahead.
We want to minimize the variance. So if you are adding a lot of polynomials, the variance...
Almost. Go ahead.
My thought was the size of the coefficient. Like if it's larger, then it's probably relevant. If it's not.
As you want to look at the coefficients, I assume one might do that. He was a little bit closer to the way that is conventionally done. Yeah.
But going beyond the cube, just basically be more twice stretched versions of cubes and squares.
No. Yeah.
Would we be looking at generalizability and easy dimension problem?
Possibly. Lisa?
Well, in machine learning, what people do is often like split their data set between a test set and a training.
Yeah, so we could possibly go a machine learning where we train the data set. We're not going to do that for this because we actually have a theory which helps us think about that directly without splitting the data set. What we can do is exactly what we did for kernel. It's exactly the same problem. He had about half of the answer. The other half is that, well, we have the variance. You know, the more polynomial you add, the squigglier our function is going to be. On the other hand, we also have bias because we don't know the actual shape of the function. So if we don't do enough polynomial, we have bias. So we need to minimize some combination of bias and variance. What is our standard way to do that is mean squared error. So we're going to try and minimize mean square error. How do we minimize mean square error? Exactly like we did with kernel regression, which is we're looking at a cross-validation criteria. We calculate the sum of the estimated mean square, and at some point we stopped when we have enough polynomial. So so that's exactly how we're going to pick the polynomials. Other than that we need to pick the polynomials, the behavior of this linear expansion is very, very, very similar to OLS. So the theory is a little more involved because we have bias that remains, but the bias will go away as you add more observations, and it goes away, and the variance, of course, will also go down as you add more observations. So basically, it's the same idea as kernel. With the kernel regression, what you promise to do is to reduce the size of the kernel of the bandwidth as the number of observation increases. With polynomial regression, with series expansion, what you promise to do is to add more polynomial as your number of observation increases. So it's exactly the same principle. And the nice thing of that is that that's very easy to manipulate in theory and in practice because it's just OLS. So it's even simpler than doing a kernel regression. Although, I mean, at the end of the day, it's R who does it, so R does it kernel or a series. But in terms of manipulating, it's easier to think about it. So it's very easy to take the derivative of this. Therefore, you can, if you're interested, once you've estimated, you say, oh, suppose I'm interested in the elasticity of demand with respect to the price. You can get it straight from the function by taking the derivative.